all the audience here. And we heartily welcome you, sir, here. And we wish sometime you visit us physically. And you have taken a very important topic for your lecture. That is reconfigurable intelligent surface, communication, localization, and sensing. It is a very timely topic, which is going to help to develop a lot of IRS system in future. And I'm sure all the participants will be highly benefited by your distinguished lecture from IEEE ComSoc Society. And again, on my behalf and on behalf of department, on behalf of institute, I warmly welcome you, and we are looking forward to your fascinating lecture. Professor George.
So, thank you, Pritam sir. And now, Professor George, we are just very eager to hear you on your topic. So just a request for participants, during talk, if you get any questions, just put in the chat box. We will take your questions for discussion one by one after the presentation or during. So now, George, I am offering this platform to you. So George, please go through the talk. Now it's all yours.
So hello to everybody. Professor Singh, Professor Kumar, thanks a lot for this invitation. I'm actually very happy to be remote with people from IIT in Patna. Actually looking forward to have the opportunity to visit you there and actually interact. It should be great. So let me share my screen. And so Amit, can you please give me permission to share? And I can go with the slides.
It's allowed, please.
Okay, so let me know if you see the slides.
Yeah, it's visual.
Okay, full screen so I can start.
Yes.
Okay, so once more, thanks everybody. Just again, some things regarding myself. My name is George Alexandropoulos, and I'm actually assistant professor for wireless communication systems and signal processing at the National Kapodistrian University of Athens, which is shortly known as University of Athens. It's actually the oldest university in Greece. And I'm actually hosted in the Department of Informatics and Telecommunications the last 3+ something years. Before I was in industry, as Amit said, in Huawei, in the Mathematical and Algorithmic Science Lab in Paris. So my expertise is actually, just to emphasize that, on signal processing for wireless communications, especially on the physical layer, on various versions of multi-antenna of MIMO systems, actually in general, ranging from massive MIMO, hybrid beamforming, relevant approaches, full duplex radios, etc. And the last 4 or 5 years, I was part of a team in Huawei, among the first around the world, where we started working about this topic of reconfigurable intelligent surfaces, which are actually meta surfaces intended for wireless communications. Just for your knowledge, it's a topic that has been used for some years before in other disciplines like imaging, like wave propagation control, mostly inspired by physics, but mainly last year's is actually really actually a topic that involves many people working in wireless. So I'm going directly to the meat with some general descriptions, and then we go to the specific technologies of the surfaces. Another thing that I would like to know that I would like to share in the beginning of this distinguished lecture is that the emphasis is mostly on the signal processing aspects, but definitely I will talk about hardware architectures for doing RISs, and I want to emphasize that I'm deeply interested on the interactions between hardware and algorithms. So you will see many times that many ideas that have to do with actual hardware of metasurfaces popped up from some algorithmic needs when we were thinking about wireless communications. So we know very well we're actually living in the era of 5G. The deployment of 5G is actually spreading around the world, and we have various fascinating applications which definitely seem to drive research in the sense that many needs are being created, and we have to follow it up and to satisfy them with, next generations of wireless communication systems. Here, I'm just indicatively include some figures just to emphasize the various vertical applications that they have been enabled by 5G, which actually introduced more or less mainly the topic of Internet of Things. So devices, many of them with very low computational and storage capability to be connected all over the world and provide a lot of data. So we have these new applications of autonomous driving, the Industry 4, which was one of the core applications that drive 5G, and of course applications that are, let's say, not so widespread, but they're actually spreading, and they will be more pronounced in the future, something like smart farming or smart houses. Let's try to emphasize to all where we stand right now. As I told you, I've been involved with wireless communication as wireless communication standards the last years. And this is a timeline taken from 3GPP, the third generation partnerships project, which actually handles more or less the different releases of the wireless communication standards. And I would like to emphasize here and actually note to everybody that the release 17 has been actually very recently frozen in March 2022, which means that the release 17 has been defined, well defined. It's actually, we're now in the case where start deploying this release, but there's also the focus on the release 18, which has also started, which is the 5G advanced. For those that have been involved in wireless standards before, we recall the LTE, the core generation of 4G, which was then actually passed the floor to LTE advanced. So more or less, we're in a similar situation where we're thinking about what's next in 5G, which will definitely introduce the 6th generation standard, which is supposed to be out there around the end of 2020, so around 2030, the end of 2030. I want to emphasize that it's interesting when we see what is happening within the release 18, which is a list here you can see of potential technologies that actually they're going very well and they have found their position into the standards already. But there is the vision to be extended more. And I want to emphasize, if you look at the right part of this slide, where you see the RAN, the radio access network, just to emphasize, especially on the physical layer, which is going to be the focus of the talk today, we see that we're still expecting of evolutions on the new radio that 5G introduced on MIMO, and especially on massive MIMO. There is this introduction of AI and machine learning in the end interface, which means that using sophisticated learning techniques on the physical layer to do stuff. There is the evolution of the duplex operation that lately we see also the technology of full duplex to kick in one way or another, which is the technology that envisions simultaneous transmissions and receptions in the same time and frequency slot. But also I want to emphasize, of course, we have things related to positioning, new stuff that are being there. You will realize that somewhere there is the notion of the smart repeater. So this is a bullet. I don't know if you can see my cursor. There is the bullet that calls smart repeater, which seems to be let's say, the initial introduction of the smart surfaces, of the configurable intelligent surfaces into the standard. Just to a bit of history here, there has been the notion of relay, and I will discuss more or less the differences between relays and reconfigurable intelligent surfaces, which I will abbreviate as RISs from now on, from the initials, reconfigurable intelligent surfaces. Relays, they were part of the standard even for 4G, but for various reasons, they didn't really go through, which means that it was there, but we have not seen many relays being out there for hardware issues, for resource allocation issues, etc. And of course, the extra cost that it was envisioned to be incorporated into the network. With relays, we are thinking something close to a base station, to an access point to be incorporated in order to provide, let's say, extended coverage. But the smart repeater, which is something that the relay plus, where the RISs, they hope to play a key role, is the idea of having something like a relay, some coverage extender, etc. We have various applications of it that are cost power and hardware footprint efficient. And this is actually the emphasis that I would like to pronounce here, and actually going slow and so into the reconfigurable intelligent surfaces. But before going to that, I would like to emphasize that if you see here this figure taken from NTT Docomo very soon, actually 2 years ago, and you see the trend on the evolution of the wireless communication standards. Of course, you see the key technologies in the various generations. I want to emphasize the part that we're going, as far as the physical layers is concerned and the number of antennas, we're going towards more massive deployments of antennas, densification of nodes, which means that the actual distance of the wireless link gets closer, transmitter and receivers get closer, and we're going towards higher frequencies. Why? Because we have the need for rates, for more rates, which can be actually addressed really well if we provide higher frequencies, because there is actually free spectrum that we can utilize there. And the fact that we're densifying, nodes are getting closer, this is actually of profit to the higher frequencies which have exhibit high penetration loss, and this can be actually treated well if the distances are closest. Of course, there's the need for intelligent algorithms to learn, predict, and adapt. But as I said before, we need cost and power efficient transceiver hardware to make this a reality. Some many speculations regarding 6G. So there's a list. It's actually not a fresh list, but it's still out there. It's taken nearly 1-2 years ago, where people were already speculating about what 6G is going to be. Recall that 5G has these 3 core use cases: the enhanced mobile broadband that targets high data rates, the massive machine type communications that targets huge connectivity, right? Various IoT devices to be connected. And there is the URLLC mode, which is the ultra reliable and low latency applications like remote surgery and autonomous driving, where we want actually increase guarantees in terms of reliability and latency. So these things actually in 6G are being are already speculated to be much more pronounced. So we're looking about just indicatively to show some values that you see already here to discuss them. This 100 gigabps till 1 terabit BPS peak data rate per connection. We have this requirement for positioning accuracy either as an end service, because we want positioning to localize a user, or because we want the positioning to be a key ingredient of our operation. So tell me your position. I need your position exactly in order to direct, for example, my beam, my transmission towards you. There is this extra need for even more demanding radio latency. We have the need for energy efficiency, nearly batterless IoT devices, density, ultra reliability, and various stuff. The key question there is, can we continue scaling the number of antennas and densification in order to achieve these goals? The problem is densification creates interference, which is something that we need to handle. And the fact that if we try for increasing the number of antennas, this has cost, power, and hardware footprint issue. So we need to do something much smarter. So here comes actually the need for cost and power efficient transceivers, or at least radiating nodes that have this capability. And this actually drives me to the outline of the presentation today, which is actually mainly shaped around the technology of reconfigurable intelligent surfaces, its fundamentals in modeling and channel estimation, which is one of the core problems with this architecture. I will also highlight some recent applications of recent enabled smart wireless environments, and I will explain what is this notion of smart wireless environment. I will conclude with actually various open challenges and research directions. So let me start with a brief introduction about what is a smart wireless environment. Here you see a figure from one of the papers that we had done with various colleagues in the open literature nearly 3 years ago, 2019, where you see a typical, let's say, deployment of an operator's network. Comprised here, you see 2 base stations, and there is a specific UE, this user here, this mobile handset, that tries, to connect with a network handled by a single operator, let's assume at this stage. What is really happening up to now is the following. There is the physical environment that incorporates, can have objects, buildings, as you see there, that creates the geometry of the signal propagation, reflection, etc. And the user will connect to the base station that receives the strongest signal. And here you see, please take the distances of this figure as you see them there, which means that the base station 2 is much further than the base station 1 from the mobile handset. One, naturally, there were no objects. We think that due to distance and due to path loss, the stronger signal would be from base station 1. But let's consider in this case where there's this object 2, this building with these chimneys there, which actually obstructs the direct signal from the base station 1, which at the end of the day results in an occasion where the strongest signal comes from the base station 2. This is actually, in terms of thinking about communication networks, there is the RAN control, the radio access control, that takes the decision who is the base station that provides the best signal, base station 2. So the user is connected there and the service is actually initiated. What about if we were having these obstacles, apart from being as they are, passive and uncontrollable? I mean, they're just, let's say, their intervention in the wireless propagation environment is determined only by geometric optics, the pure laws of physics. What about if we were capable to manipulate the way reflections are happening in the environment? This, and consider that if we could do it, what about even having the possibility to program jointly the reflections from objects in the environment and the configuration of the base stations? Could be, for example, the beamforming on the antennas, right? How could this be done? By the technology of reconfigurable intelligent surfaces, by coating objects, their surface, with some reconfigurable material, would give us the possibility, right, to tune its reflection characteristics in order to provide reflections that are programmable and they're at will, right? We can optimize it in order to achieve our goal. Of course, we would like a dedicated controller to do that, and this controller should be part also of the RAN to be jointly optimized with the base station. So consider the case that you have an operator, it has these two base stations, right? And it also owns a couple of surfaces, right, that are coated in the available objects of the environment that they can control the reflections and we can optimize them. So in this case, we could go, we could end up in a scenario that you see exactly in this figure, where we have the base station 1, which is the closer, right, naturally, which what we're expecting, profiting from tunable reflections from nearby metasurfaces in order to provide a much boosted in terms of achievable, let's say, performance metric, the desirable one, performance. So this is the notion of the programmable signal propagation with the enabling technology to be the reconfigurable intelligent surfaces. I want to emphasize here that it looks cool, it looks interesting as a topic, but there are two major things that one needs to overcome. One is related to the fabrication of these metasurfaces, which actually we have very good technologies already ranging for few actually megahertz, gigahertz, up to terahertz lately. There are projects that are working on that, right? But the other major issue is their incorporation into the network. How we incorporate the network, how we talk with them, and how we optimize them. At the end of the day, this is a personal opinion, and which I believe it's shared actually by various experts working on the topic. This is one major thing that needs to be overcome, how to efficiently incorporate the network. And this is actually one of the main focuses, apart from the fabrication that is being handled by various people working on the topic. As I said before, at least to me, it sounds cool to have smart wireless environments, but how? As I said before, there are available metasurfaces ranging from few megahertz to terahertz, and they're actually operating at the basic level of propagation of the waves, and they're capable of tuning the impinging electromagnetic field in the RF domain. So everything happens in the RF domain. We don't need to do things as we normally do in transceivers. I mean, we transmit a signal, and before doing that, we have bits in digital form. We need to have a transmit RF chain, right? to upload the signal on the frequency of the communication, send it. But before that, we need encoding, we need modulation, all these things. And let's say the inverse operation needs to happen at the receive side. Actually, the idea of reconfigurable intelligent surface is that they're actually super simple, and whatever processing they do it on the analog, on the radio frequency domain, which means that they're not supposed to do at least the initial proposal of metasurface. Today I will present you also various other architectures. The idea is that they're not capable to do data decoding, not even received waveform decoding. They cannot do conversion from RF to baseband and vice versa, and nor baseband signal processing. And in this figure, you see their basic operation. If you see, for example, here the theta, which is the angle of incidence of this T transmitter of this mobile handset, what will happen if you consider that there is an object here, this O that you see there, the reflection is going to be determined by the law of physics, which is actually Snell's law, geometrical optics, which means that the reflection angle would be equal to the angle of incidence. But the key idea of coating this object with a metasurface is to provide tunable reflection. This is called lately as the generalized Snell's law, which is actually something that we can optimize, meaning that for a given angle of incidence, we can provide any reflection angle possible by tuning the elements of the metasurface, and we'll exactly discuss what is it about, what is this structure and how it is comprised. But before doing that, I want to acknowledge this is actually a big European Horizon 2020 project that is actually working on, and I'm the PI of our university, which is actually envisioning this technology for the smart wireless environments in order to enable this notion of smart wireless environment as a service. So the environment is a service. That means you can optimize it and you can do whatever you want. And the key idea there is to do this optimization in an efficient way. And this is actually what we're trying to unveil in this project, which is actually in the middle of its duration. But we also want to use this environment in order to provide performance boosted areas, meaning areas highly localized boosted performance that can be really conflicting, I mean, the one metric from the other, meaning that you have a smart wireless environment and you use it as a service, providing, let's say, a location where you want increased localization. Consider, for example, a smart factory, right? And where automation is needed. You have a location where you would like a low electromagnetic field exposure, for example, could be an office, right? Cases where you have boosted secrecy. Could be, for example, envision a big train station where you have a room where people can go there when they want to have very, let's say, sensitive information to do communication, or even other conflicting KPIs. This is one of the major things. And I didn't mention the train station. I mean, by luck, this is one of the major trials that this project is actually emphasizing to showcase this smart wireless environment as a service enabled by reconfigurable intelligent surfaces in two actually field trials, one in Rennes station in France and the other in the premises of the industry of CFR, which is actually Fiat's, the automotive in Italy. Right? And just to see some stuff on what we could do actually before going deeper into the details of the technology, what we can do with it by using a metasurface. Consider here a toy example where we target to provide by using a metasurface spectral efficiency boosting. And you see here in this deployment, which is actually, you see the 2D equivalent, the third dimension is not incorporated here. Actually, all the details are part of a deliverable of this project, which soon is going to be actually available online on the website of the project. Here you see the details of the website. There is actually a base station which is placed on the origin, right, of this coordinate system that you see. There is the reconfigurable intelligent surfaces, which has a number of elements here. The number is not, it's not the issue here. It's less than 100. And there is an intended receiver. And what we want to do, and the base station is actually multi-antenna. We want to jointly optimize the configuration of the antennas of the base station, right, and the reflection coefficient of the RIS in order to boost the spectral efficiency, in order to provide boosted spectral efficiency, achievable spectral efficiency to the receiver, compared to the case where there was no risk. So what we're going to actually compare here is the case of the specific placement of the users, considering Rayleigh fading channel, which means strong line of sight components, but there is also some scattering involved there. The Rayleigh K factor is of the order of 13 dB, which is actually a normal case, especially when we're thinking about millimeter wave, I mean the application of it. Here you see the case where we only optimize. There's a heat map where you see what is happening in the rate in all the points of this grid. Where we don't have an RIS and we optimize the beamformer, we're actually doing an MRT, maximal ratio transmission, from the base station to this nominal receive position, and you see the value that we can achieve. This is nearly 30 bits per second per hertz. I want to emphasize here that in this toy example, we use 3 GPPs path loss models for the distances that you see there. Everything is in the grid is in meters. And let's see the case where now we deploy a RIS and we actually optimize it, right, in order to boost the performance. And we can see that we can get up to 15% performance boosting by just optimizing the reflection coefficient of the RIS. Of course, the end result will depend on the specific placement of the nodes, etc. But what I want to emphasize here is really tricky. If you see there the heat map, that the base station, what is actually doing is boosting its beamforming toward the RIS to do the reflection towards the placement of the receiver. Actually, there are many works that are working also in the optimal placement of the RIS, and what we know already really well from theoretical works is that it makes sense to place the RIS either close to the base station, to the transmitter, or close to the receiver. But let's now dig in the technology. I mean, what is it about? What is this RIS? I want to emphasize before going into this discussion that RISs are also known with various other terminology, like intelligent reflecting surfaces. You have seen something like RIS is abbreviated, programmable hypersurfaces, metasurfaces, etc. So there are these 4 abbreviation acronyms that have been used in the wireless communication community, which are more or less it's actually the same terminology. Of course, the hardware will determine the differences, and this will be described later on. So surfaces, they are comprising by metamaterials, or these unit cells are they called, or there is this notion also of meta atom, which is usually constructing by arranging multiple tunable elements. There are various technologies there that also, depending on the frequency, they could be PIN diodes, varactor diodes. Depending on that, you have different modes of the tuning of the reflection coefficient. It could be discretized or continuous. And actually, these elements, they are actually placed in repeating patterns, and their inter-element distance is usually much smaller than the wavelength. It depends the application. For example, just to emphasize something, it has been shown that in applications where you want to deploy an RIS in rich scattering scenarios, you don't really need to place the meta atoms closer than lambda over 2. You don't gain much. It does not really make a lot of sense to do that in terms of the achievable performance. Although, on the contrary, if you envision environments where you have strong line of sight components, then it makes sense to have unit elements of the surface being very, very closely spaced in order to provide this reflective beamforming gain. Now, thinking about these meta atoms, the shape, the geometry, the size, and the orientation, as well as the arrangement of these unit elements, enables the smart properties of the metasurface in manipulating the impinging electromagnetic waves. And we can have actually various operations, like using the surface to do blocking, using the surface to absorb the signal that gets into it, to do enhancing, this boosting that I said before, or even bending the waves in order to achieve, right, the benefits that go beyond what is achievable with conventional materials, which they don't have artificial artificially manipulated properties. So each meta-atom is usually controlled independently, although there are implementation where we can control group of meta-atoms in order to achieve the desired characteristic. And usually what we're doing when I say about characteristic could be the direction of propagation and the reflection. This is actually what we're tuning. But what is a metamaterial? Actually, metamaterial, most probably, most of you know already very well, is any material that is engineered to have a property that is not found in naturally occurring materials. And actually, they're usually engineered, right, to have the electric permittivity and magnetic conductivity that can enable the control of electromagnetic wave propagation. And this a typical example of a metamaterial is this negative index metamaterial, which is characterized by a negative index of refraction, which is not commonly found in nature, I mean, from natural materials. And how do they work, the RISs? They are actually the impedance or the electromagnetic response, if I'm allowed here to say it more generally, of their unit cells is modified using this dedicated of the cell's electronic components, the PIN diodes or the varactors, could be liquid crystals or micro electromechanical systems or other software-defined metamaterials. This is also the technology of fabrication. It depends highly on the frequency, right, of the operating frequency, the intended operating frequency on the surface. Each unit cell or group of cells acts locally to the phase, could be also to the amplitude. Usually there is a coupling between the phase and the amplitude of the reflection coefficient. And we can tame actually by tuning the properties of each of these elements, the electromagnetic field that impedes on the surface, achieving various applications. They are available, as I said before, various proof of concepts for using metasurfaces for beamforming, for reconfigurable holograms, diffuse scattering, or even over-the-air computing lately, to do analog form of computing, which is a rather fascinating application of metasurfaces. And they actually, of course, this depends on the technology. They can be ultra low power, meaning that you can have a unit cell operating at 50 microwatts. Of course, if you multiply with the number of elements, you will get a number that's much higher, and this will be determining about, I mean, you're going to have a target power, and one will decide what to use at the end of the day. Here I'm showcasing one of the first works that actually provide the proof of concept of a 0.4 square meter RIS comprising 102 cells and operating at Wi-Fi frequencies 2.47 Hertz, where each cell was consisting of a rectangular parts that was coupled to a parasitic resonator and was controlled by a PIN DN diode. The parasitic resonator was actually capable to reflect the impinging electromagnetic field with only two different phase shifts, providing reflective beamforming, 0 on pi. So if you think of what I said before about the different states of these meta-atoms, in this case, the state was completely characterized by 1 bit. So only 2 values of using this specific case. And actually, here you see on the bottom the first paper that did that, an invited article on a newsletter that we have provided some years ago, where actually we summarize all this activity related to the potential of wave propagation of control that metasurface provide. You see an application of the metasurface in providing spatiotemporal focusing, which means focusing of the signal in time and in space. Here we see the spatial dimension. And in this case, the receiver, there is a transmitter, there is a RIS. We optimize on the fly, it's connected with an Ethernet to the transmitter. So we don't really care about doing efficiently the optimization. When it was done, the goal was show what we can achieve with the surface. And there was a very simple genetic algorithm playing with a different configuration in the RIS in order to find the configuration that boosts the transmitted signal exactly to the position of the intended receiver. You see what has happened in the case where you have only the transmitter, it was a horn antenna, indoor setup. What has happened in the position 0.0, you see a heat map, right, of the received signal strength without having a RIS. And what is happening on the right, where we have a RIS and we optimize this reflection coefficient. And what we can see there is that there is this yellow spot in the middle, which has a resolution, if you see, in the order of millimeter, right? Showcasing this spatial focusing of the transmitted signal to the intended position of the receiver. So this is one of the first done in 2014 by colleagues in France, showcasing the spatial focusing capability of using metasurfaces to manipulate signal propagation. Another application, much fresher work in 2019 by the same group of people in France, they used the metasurface for a completely different objective. Instead now of trying to focus the signal of the physician position, they used the metasurface in order to increase the effective rank of the channel. So initially there was a base station, a transmitter, a receiver, a strong line of sight channel within an indoor setup, and there was a surface playing with their configurations, right, in order to increase the rank of the channel. This is a statistics related to the channel, but it's super important, implying the following, that here you see what is happening with iteration number. There was an optimization that took place in order to optimize the risk. And at the end of the day, it means the following. You have a channel which is purely loss, and you incorporate in a metasurface that you can optimize in order to make it reach scattering, increasing the effective rank of the channel. And we know very well when we're thinking about communication theory is that we can provide, the capacity of a rich scattering channel, it's much larger than in the case where we have a pure loss channel. By applying MIMO techniques and this spatial multiplexing. And this is actually very much connected with the effective rank. So in a way, we change the propagation characteristics of the channel from Rayleigh to Rayleigh in order to enable, for example, boosting of the spectral. Apart from that, let me see here. For some reason, let me try to remove. Anyway, I have this, this element that shows the mute, stop video, etc., which obstruct some parts of my slide, but no, there's no problem. Here you see the case of the passive RIS. You see the fabrication, again, from the same group. And you see the results of a very fresh paper that we have done with colleagues, where we were actually, one of the things that we were wanted to see in this paper was the range of frequency that this specific fabrication, recall 2.47 gigahertz, 102 elements, 0.4 square meter surface. What is you see here the standard deviation of West1 2 parameters of the metasurface, implying the range of frequencies, which is around 400 megahertz, which is quite high if you think about 5G right now, especially sub 6 gigahertz. We have this 100 megahertz there in Wi-Fi. This is more or less the range of frequency in wideband operations that we have, which means that you can have a metasurface of this form, providing, let's say, an operation which is quite wide in frequency that you could use to do multi-carrier OFDM kind of communication. So there are various works that are trying to characterize the range of frequency that the metasurface is operating. And recently in this RISE-6G project that I introduced before, we have actually working on the definition of a term called bandwidth of influence, which is the bandwidth that the metasurface can influence. Of course, this will determine the actual operation, right? I mean, what we can do, how wideband it can be, but also I want you to think something more even crucial there. If we think about surfaces being used and deployed in the network will have multiple operators, right? Which means that if you have a surface owned by an operator that might influence the bandwidth, right? That is actually given, paid by another operator, this is something super crucial that needs to be accounted for. So there is the bandwidth of influence that we're investigating there. And actually it's of detrimental, actually of paramount importance to determine the actual application in a multi-operator network of metasurfaces. Now, moving a bit further, apart from the passive metasurface that I told you before, passive are the following. You have pion, diodes, varactors, very simple circuitry that controls the the reflection coefficient of the metasurface, and you have probably an FPGA microcontroller, right, that needs to communicate with the network in order to take the decisions what to do, when to change, to synchronize the reflection coefficient, but also give actually the order to each specific element of group of elements to change the reflection coefficient, right? Everything happens in RF, we just control the reflection coefficient. This is the so-called passive RIS. As you can understand, it's not passive. It doesn't have zero power. It requires some power, but it's rather low. It's only, there are two things there that determine the power consumption. The change of the reflection states of the elements and the communication with the rest of the network. Lately, there is a lot of work in actually making them even smarter, and I will try to identify later on why is this needed. Because actually, if you don't really incorporate it, when you try to incorporate to use them in the network, you require a lot of overhead to communicate with it and optimize it. So people lately, including my group, they're trying to think of extension of this technology, keeping the part that has to do with the RF, let's say, manipulation of the reflection, right? But also make it smarter in order probably to sense, to estimate something, to boost its self-adaptation. This is the actual intention. And here you see one of the first works. That was an invited paper 2 years ago in ICAST, where we introduced the notion of having the metasurface, but plugging actually a portion or even all the elements, their combined output by using specific waveguides to guide what is actually being received, what impinges onto the metasurface, and drive them with a waveguide to a reception RF chain that is intended to measure something, to send something related to the impinging signal. For example, to do a form of channel estimation in order to use it to do the optimization of the operation. So this basic, let's say, conceptual proposal there was the following. You have a RIS with different elements, and you have their combined output fed to either multiple or single typical receive RF chains, like typical receivers have, comprising by a low noise amplifier, a mixer, and analog to digital converter. And the operation that it was envisioned there, it was to, when something impinges there, right, and you have the possibility with this circuitry to drive it to the receive RF chain, to receive it with different configuration of the reflection coefficients that could be used in order to devise sophisticated channel estimation algorithms that provide actually the estimation of the involved channels, and I will be more detailed later on. So I want to keep here that we're talking about, we have the passive RIS, and now we're talking about the RIS, which is the same or the front end, but we have a circuitry that provides us the capability to send something related to the impinging signal. Of course, this will impose power, extra power to run the reception RF chain, and this will determine on the number of RF changes. And of course, this will have further hardware footprint, right, in order to do that. But you will see later on that we can do it with only one RF chain, and I will show you how we can do that. Apart from that, very recently, we, together with colleagues from US, we have actually fabricated a meta atom which is capable simultaneously to provide tunable reflection, right, but also absorb a portion of the impinging signal, which we can drive it in baseband through a reception RF chain to do any form of estimation of this specific signal. So more or less what is being happening is that there is a splitter there that provides this power splitting of the reflection tunable reflection, and a portion of it, a portion gets reflected tunably, and a portion of the impinging signal with a specific waveguide, which is coupled with the element there, drives the portion of the signal that impinges to a receiver RF chain in order to provide a form of processing of it. Apart from that, people are also envisioning other architectures. This is closer to the passive, but still, this is still conceptual. People have not really proposed how to realize that. Where now we're thinking about not having the surface providing service only from, let's say, 180 portion of the space, but also on the back of it by having this so-called reflective and the transmissive RISs, but they also called it reflective and refractive RISs, in the sense that you could provide tunable refraction and tunable refraction from the other side. And one of the major applications using that is by having it as a way, let's say, to separate rooms, or even having glasses. Consider these big buildings made of glass, where the glass is a metasurface and can also provide form of reflection to outdoor users from a base station, but also boost the refraction of the signal coming from the base station internally to indoor users. Apart from that, there's also recent work that we have done with colleagues, where we're envisioning, and there are also some others from other group, that apart from doing reflection, they're envisioning ways to do reflection amplification. And one of the reasons for doing that is that the typical operation of the surface up to now that I told you before, even if it's passive or it can sense whatever, the reflection part does not provide any, let's say, power gain. The problem with this is that we have the issue of the dual path loss, which means that the signal, when it will go through the wrist, gets reflected and then to the receiver. And usually this path it has a length that results in a path loss which is super, super low, right? Which means that the surface should be, let's say, applied in scenarios where it's close to either the transmitter or the receiver, and the distance between the transmitter, the end-to-end distance is actually low. So people are thinking of effective ways to provide amplitude amplification, but we don't, please recall, we don't want to reach the other extreme, that at the end of the day, we have a relay, which is a massive MIMO antenna. We want to do it smartly, right? So here we're envisioning a work where we have, let's say, 2 RIS, could be one, but some portions. And the idea is to incorporate a variable gain amplifier. What gets actually received being directly amplified with this. This is again conceptual. We don't have a proof of concept yet. We're working on that, and being fed to another wrist that provides this reflection amplification. What I'm trying to tell you is that there are various architectures that are trying to resolve the issues that have been identified from the years that the notion of passive RIS, which cannot be passive, as I told you before, has been actually conceived. Apart from that, I want just to be, in order to be complete to that, there is also a recent trend lately that envisions the usability of the adoption of metasurfaces, right, as the next generation extreme massive MIMO antennas, which are, this is in a way similar to what I said before, but here the notion is the following. Instead of having typical antennas at the RF front end, you have a metasurface. You have a typical metasurface, and this metasurface is attached to either transmit or receive RF chain, actually providing the so-called metasurface-based massive MIMO transmitters on receivers. And the way they operate here, if you see, this is the way we have microstrips, comprised of microstrips. Each microstrip has these unit elements that we said before, which can be controlled analog domains, like having this analog beamforming, like with the phase shifts that we had before. And there are specific wave guides, these feed ports that provide whichever signal goes to either, consider, for example, the reception case, right? And drive it to a receiver RF chain. There is, according to this proposal, together with a group from Israel, we have been working actually intensively in providing modeling of what is happening within the microstrip for the metasurface in order to use it and optimize it, and how we can do signal processing with it. So apart from that, I want to complete and finish this discussion that there is also the notion of providing, using the metasurface in the RF front-end to do actually to fabricate metasurface-based antennas. There is this technology, which is actually various technologies of metasurfaces. The cool thing is that there are fascinating applications of the technology. Some of them are rather conceptual. Some of them are actually much closer to practice, which means, and I want actually here to advocate the challenges and the assumptions that people have in mind and how this can be resolved. Here you see actually a a figure taken from a recent paper of ours where we were actually envisioning this holographic MIMO surface concept by passive hybrid RISs like used for antennas or even typical transceivers to be used for various applications, boosting energy efficiency, physical air security. I have a specific example to discuss later on, or even do power transfer through the surfaces, or even use energy harvesting to empower the surfaces on their own. By the way, this empowerment of surfaces with energy harvesting and make them capable to sense, as I said before, with this hybrid beamforming, this drives the notion, the recent notion of the autonomous RISs, which can be power and computationally autonomous to do various stuff. The applications are actually numerous. They are booming lately. People have been using RISs to provide localization and positioning, actually, and we discussed how this can happen, to provide secrecy, cognition and sensing, wireless power transfer, their usability with UAVs, or even use them, right, as a means to modulate information, modulating, for example, this reflection modulation. Even the reflection that is being done the metasurface could be convey information and could be jointly optimized, right, with the information encoding that is being done at the base station. Now, let me dig in the fundamentals of the RISs, emphasizing the unit cell modeling. Some models, there is ongoing work. I'm going to present one of them. We have an ongoing work, still not ready yet. I will give the hints, but the details we're going to come soon. I mean, we're going to disseminate them. And of course, the channel estimation, which is one of the major issues, and I will discuss why is a major issue. So one actually well-accepted model being used is actually the one that you see here, which is a transmission line model that tries to actually model the behavior of the RIS, right? Here you see a point source, which could be an access point. There is the transmission line, which is actually the air, which is the interface, is the medium, right? And there is the incident and the reflected signal. And in this work that you see there, people are actually modeling the reflecting element in the form that you see here. They have a typical RLC circuit, right, with some tunable coefficient. I want to emphasize here, and this is actually starting using notations to use later on for the mathematical derivations and the algorithms. Let's consider this phi, which is actually a Greek letter pronounced like phi. I mean, the typical way we pronounce it here, which is comprised by n elements, and consider that n elements is the number of elements of the RIS. So this vector includes the configurations, the reflection coefficient of the metasurface, which is comprised of discrete elements, right? And based on this model, each element can be expressed with the form that you see here on the bottom, with this zeta n, which is a function of the Cn and Rn, and this zeta 0, which is relating to the air. And here are the definitions of all the involved parameters. The Cn is the effective capacitance, the Rn is the effective resistance. There is the zeta 0 that is the free space impedance, and there are some other elements related to this specific model. With L1, it is the bottom layer inductance and the top layer inductance. And there is, of course, the omega, which is the angular frequency of the incident signals. Here you see, we see the frequency response of the reflection coefficient, which follows this transmission line model, right, which is at the end of the day parallel resonance circuit with impedance. This is one of the ways that people have been using to model the reflection coefficient. What is the basic RIS-empowered communication system that I would like to emphasize here and provide some further rotations that are related, will be actually the baseline, the core elements to be used in the algorithms to present it, to be sketched later on. Consider that you have here a transmitter, you have an RIS, you have a receiver, and let's assume here that we have this H1, which is a vector with the channel gain coefficient between the single antenna transmitter and the multi-element RIS. Similarly happens from the other side between the RIS and the receiver. And let's assume that there is also this channel gain, which is a scalar between the transmitter and receiver. We will extend later on to the case where we have multi-antenna transmitter and receiver. And consider the case of where the transmitter wants to communicate with the receiver. There is the risk that we can tune its coefficient, right? You could envision various extensions, multi-antenna transmitter receiver, multiple RISs, right? You could do various stuff, or even RISs being simultaneously used by multiple transmitter receive pairs, or even owned by a specific transmitter receive pairs. This actually, you can think of cases where there are operators, right, using their own RISs, or operators that are actually sharing RISs. Have this in mind. I will discuss at the end of the talk today. So consider this planar RIS is equipped with knee elements, NV elements in the vertical axis, and H on the horizontal axis. And in general, we can have a direct link. Just to emphasize here, the RIS, as we know up to now, theoretical works, but even in the proof of concept, makes sense when this channel, this A channel, the direct channel, is rather weak. For the reason that I told you before, this dual path loss from the path that goes from TX to RIS and RIS to RX is going to be much higher than the H. So usually when the H is attenuated through an obstacle, right, then the deployment of the RIS makes sense. Otherwise, you don't really gain much, even nothing. Let me continue with the modeling here, the way we use it to do signal processing. Let's construct this phi, which is a diagonal matrix here, has the elements of this non-capital phi vector in the main diagonal that has the effective phase shifts of the elements. And let's assume, as recall the previous proof of concept, that each element of this of the diagonal of the phi matrix takes values from a predefined set, which is actually implies the different reflection states that each reflection coefficient have. This is a typical, let's say, way to write the code book of the reflection coefficient. And this beta B here determines the phase resolution in number of bits. And usually the way we model the amplitude is 1. So there is no amplitude amplification there. Although in practice, if you consider this transmission line model, there is a correlation between the value of the amplitude and the value of the reflection coefficient that it takes. We define this H1, H2 just to proceed, and there's also the signal that the transmitter wants to send, the complex valued in principal information signal, which is taken from a discrete modulation set. And of course, there is a thermal noise right at the receiver, at the reception. Let's assume that has variance of sigma squared. So the typical baseband received signal model that people have been using in this field, right, is of the following form that you see here. And for simplicity, I have removed the direct transmit receive link. Recall this H scalar that I had before. So the received signal through the RIS is of this form, and this is known as the cascaded channel model. I will actually challenge that just in the slide that follows, where actually what is really happening is the following. What is being received, and this is the equivalent in baseband, right? What is being received at the RIS is this H1 times S, recall H1 times S. There's no noise. We don't go to baseband. There's no thermal noise. And this actually, what is happening here, this signal, it gets directly reflected by the reflection coefficients included here in this diagonal 5 matrix. Actually, what is really happening, see the last bullet, what's happening is the following, that what impedes on each specific, the nth element of the metasurface is the nth element of H1 times S, and this gets reflected by being multiplied by reflection coefficient, the reflection coefficient of this nth element, which is the nth element of this phi matrix. So, and then there is also the channel that goes between the RIS and the receiver. If you do some simple manipulations, you can end up into this expression here, which is the Hadamard product element-wise product between the two channel vectors times the configuration. This is the vector that includes the reflection coefficient times the transmit signal times the plus the additive wide Gaussian noise. I want to emphasize that this cascaded channel model is actually widely used in the signal processing community, communication community, in devising algorithms for reconfigurable intelligent surfaces. So people they're using this model, they're writing down their performance metrics, and they perform optimization on the RIS and any other tunable parameter of the net. Could be also the configuration of the antennas of the transmitter, the receiver, right? This is what people are doing. But apart from that, in order to do that and devise the metric, you need to know, usually, any channel dependent approach, like typical MIMO, requires channel estimation. We need to know the channels, right? So we need to know this H2 and H1. You will realize later on that with a passive RIS, it's extremely difficult to estimate the channels. We require a lot of overhead. That's why the different architectures have been proposed, which means that we have two core issues here in deploying in RIS. One, we need to estimate the involved channels, and then we need to optimize given this information. And this drives the rest of the discussion that I will do during this talk. Apart from that, I said that this is widely spread, but I want to emphasize that this model, even if it's this cascade channel model, which we'll see later on general for multi-antenna system, etc., is an oversimplification, unfortunately. We have been using in the literature an oversimplification for this thing because in principle, the channel, it should be, for the specific toy example that I showed you before, single antenna transmitter, single antenna receiver, it should be a function of the configuration of the S. I mean, does not necessarily, and actually in principle, if you are not in nearly pure loss cases, it won't be this cascade form. You could not actually factorize it like that, and it should be the channel, in principle, it should be a function of the configuration of the surface and the transmit signal. Usually we use a linear model for between the channel and the transmit signal. At the end of the day, it should be a function of the F, which is not as simple as the cascade channel model, especially when we're thinking about rich scattering, because there are actually various bounces that might happen that actually deviate from this cascade channel model. I'm not going to go into the details of that. I just want only to drive you in a very recent paper that we have been working together with colleagues, where we present a physics-based end-to-end channel model to utilize in fading channels that are parameterized, as you see here, with a RIS, with the configuration of the RIS. So in this paper, we also provide MATLAB code for this simulator, and everything in our modeling approach follows the coupled dipole formalism. So we formulate, we model each element, either a passive object, a transmitter, multi-antenna, or single antenna, transmitter, or receiver, or even boundaries of the environment, like dipoles. But in the case of the surfaces, which are still coupled dipoles, they have tunable coefficients that we can optimize. This is a very fresh work that we have recently provided the revised version. As I said before, you can envision of generalizations of the model. So this is the case where we have a multi-antenna transmitter, a multi-antenna receiver. So this H1, if you recall, and H2 vectors will be matrices, and the direct will be again a matrix. So we need to devise all that. Of course, in this case, the signal is going to be X, in the sense that the X will include the data streams, but also will include the precoding that the transmitter can do. So this is the generalization of the cascaded signal model that I said before. Even going further, and here you see one of the first, actually these are the two first works that they, let's say, pushed together with the one that they saw at the beginning in 2019, that they pushed the idea of having and actually showcase in signal processing how we can do that, the incorporation of metasurfaces in wireless networks. Here you see the case where you have a multi-antenna base station, a RIS and single antenna users, and the intention of those papers to do this passive and active beamforming, which means the joint optimization of the precoding of the base station and the configuration of the RISs. I don't need to go into the details. These are different ways to, and now you need to extend the way you model the involved channels, but at the end of the day, the approach is quite similar. And here you see the equivalent received signal model for this case. And actually you see what is being received on a specific here user, the kth user, which is again the cascade channel model, and the X can include the precoding matrix, or even the power allocation of a specific user, and you could actually do on top of that optimization of the power that you provide in each user. I want to emphasize something more, something important here when thinking about the differences between the relay, as I said before, but the differences I sketched them before with a relay, but I want to emphasize here when we're thinking about signal processing, what are the differences? What about if we didn't have a metasurface and we had a relay? What will happen? What will happen actually when we're thinking about signal modeling, which is actually of paramount importance to devise signal process algorithms, is that the relay would impose, due to the fact that we'll receive in baseband, this WR that you see on the first expression, which is the thermal noise when it's performing the reflection, which means that this reflection, when we're going to do in the multi-antenna relay, then an optimization of the relaying, let's say, of the relaying beamforming matrix, this will also be applied into this noise term, which at the end of the day, at the reception or on the actual receiver, at the end receiver, will include this red term that you see, which was, if you recall, was totally absent in the case of using a passive RIS, because everything was being doing in baseband. So if you see this expression, the second bullet and the last, this showcases in terms of signal processing, in terms of received signal model, what is the key difference in using relays or not. Of course, we cannot easily get to an answer and say it's better to use relay or surface. It depends. It depends. What is for sure is that there are certain scenarios, and this has been discussed in the papers that I showed before. For example, here, there are certain scenarios where you can have energy efficiency much larger, even if, let's say, twofold, threefold, much better than using a relay when you deploy a reconfigurable intelligent surface. But of course, keeping in mind that all the orchestration, we keep it ideal. Of course, this, at the end of the day, this needs to be incorporated. Here you see a summary of the things that were said before, and even before that, related to the actual, let's say, comparison between RISs and multi-antenna relays. The RIS, as we have said, they consist of possibly very large number of metamaterials, while the relays, they're equipped with typical antenna elements, which means that they cannot have massive number of antennas because they will have actually increased hardware footprint and cost. Naturally, one could tell me here, what about having a relay with a metasurface based antenna? Would it be more effective? The answer would be certainly yes. So people could devise interplays with that, and you will see it later on. The RISs do not require power amplification, at least on the passive version that I said, or even on the amplified version, people are thinking of providing even one amplifier to do the job. And actually, their operation is being applied on the RF domain. Instead, the relays, they want to do various things in baseband, which requires dedicated circuitry. This is, I emphasize one more, the comparison between passive RISs and multi-antenna relays. So you will realize that we're going towards relays in a way, right? The notion was initially for fully passive, but we have the issues that I told you before. So the passive RISs, they cannot do any channel estimation, right? Although there are, as I said, RISs that they can have a signal of your exchange to do that. The conventional relays, they rely multi-antenna relays or channel estimation in order to optimize their beamforming, right? And do special beamforming. Another crucial thing and really important is that the larger RISs, due to the fact that they'll be quite large because they're cheap, right? And they have low hardware footprint, they can enable communications or operation in general in near field, which brings forth many fascinating opportunities and of course challenges for both communication and localization. This is actually absent, this capability is actually absent when thinking about conventional relays. Apart from that, RISs, due to the fact that you can optimize in VRF and do fascinating stuff, they can be used to enable wave propagation control, even in rich scattering environments. And here you see again this work that I mentioned before, where we have been using RISs, as we call them there, analog processors, as a way to do over-the-air computation. So here in this work, we emphasize their utilization in handling inter-symbol interference in the RF domain by the configuration of the RIS, which brings forth many fascinating opportunities which are not actually feasible with multi-antenna relays. As I introduced before, of course, it's natural one to think the combination of RISs with relays, I mean, using them synergetically in order to optimize the performance, and there actually works actually emphasizing towards this direction, mainly on doing coverage extension, but one could envision certain other applications. As I said before, one of the major things with RISs is the channel estimation. And up to now, we have various approaches. People are thinking about control protocols, dedicated protocols to the channel estimation, using on or off risk activation patterns, which means they keep some elements on, some elements off in order to estimate the channel between transmitting the specific elements and the risk. Either approaches that are based on purely beam management, so this is not explicit channel estimation, it's implicit, for actually handling the channel estimation issue with passive RISs, and are actually schemes that are using RISs through their analog combining capabilities, if you recall, when they're incorporated with few RF chains. There are various groups working on that. And I want to emphasize a little here, what is the problem with the RIS, and then sketch the operation of the others, and we'll go fast to make it actually on time. Actually, this is the right point to ask you, Amit, how much time do I have?
You have about 15 minutes left, so still you can go for. No problem.
Okay. So I will speed up a little bit. I want to emphasize what's the channel estimation problem, and then I will sketch the various applications, and I have actually dedicated description of the papers that people can go and see the details. The channel estimation, as I told you, is a core issue because we need to estimate the involved channels in order, this is the required information to optimization, right? Usually how it works, here you see the least squares pilot assist channel estimation is one of the baselines. People have been working towards having more efficient approaches, but the overall idea for a passive risk, this is the case. So here what is happening is the following. Consider that we're using focus on the uplink, there's the base station, there are different UEs, and we want to estimate all the involved channels, G, capital, G1, H's, everything. The way to do it is that we deployed training symbols, right, from each UE. Let's focus on the specific UE, forget the others at the time being. And this guy is actually sending these pilots that will go through all this channel. I'm still using the cascaded channel model here. And there is the noise. And after some basic manipulations, you can come up to the last line formula where you have the unknown channel HK that incorporates all the involved channels that you see there, H small k non-capital, G capital, and the diag of GK, which is the channel between the UEK and the RIS, right? And there is this factor that you see here, which is 1 and phi t, which is the configuration of the surface at time t, right? In order to estimate what usually we do, if you realize here, if the base station knows the pilots, right, then he can come up to this expression, right, of estimating the signal. He will get the unknown matrix, the configuration of the RIS, and of course the thermal noise. What people are usually doing in the literature of channel estimation is that we deploy a number of configurations, we're changing the reflection coefficient, right, in order to create this F capital matrix, right, which is actually being used together with the pilots to get the estimation of the unknown channel matrix. Here for the LS pilots assist channel estimation, there is this F, which implies T capital different configuration, which translates into T different TTIs, transmission time intervals, right? Different time slots that you need to change the configuration in a synchronized way. And if you use for this configuration, it has been shown in this paper that to optimize the channel estimation error, you just need to deploy a phi matrix, which is comprised, it's the DFT matrix, which you can understand it needs to be the number of elements. This T needs to be equal to N, which is the number of elements. And you can get the LS estimator, right, which is given by this the number of xk, which is the known signals, the received signals time, the pseudo inverse of the DFT, which has the configuration of the RIS, in order to get the estimation of the H matrix. All these matrices there, all together. You cannot really split. You can get it all together to use in your metric. But this requires a pile overhead, which is n times k, number of users, could be in general, and n is the number of elements. So imagine that you have a surface with 1,000 elements, right? This will translate in a huge overhead, which is actually really problematic. That's why people who have been using, thinking of ways to provide low training overhead channel estimation approaches. One way is to use this parallel factor, the composition here, from tensors, to provide efficient methods for estimating multiple large channel matrices simultaneously. Or even lately, people are using actually channel estimation with low overhead, thinking of beams and beam training, some recent works. So this is a work that is related to the parafac. Due to the economy of time, I will go really, really fast on that. Just to emphasize that is an effective way one could think of using pilots and getting the estimation of the multiple involved channels. It has been shown in this works, a recent work of ours, that we can do it with much less overhead than with the others. But another crucial thing is that we have recently combined these approaches, profiting from the tensor analysis, to do both channel estimation and signal recovery when thinking of recent powered multi-user systems. Another way here, and I will again go fast, is the way to use this single RF architecture to provide channel estimation. I would skip the idea, as I told you before. You have one RF chain, you receive, it works in the receive mode. You receive with different configuration of the RIS. Pilot signals orthogonal being sent, considering one transmitter, one receiver, in the uplink by both these nodes that we want to estimate the two involved channels. Orthogonal if you want to do it in parallel. And by using a random reception of this reception and using compressed sensing tools, you can actually get the estimation of the involved channels, especially when you're operating in cases where the channels are quite specular. I mean, there's strong loss components, and this is the way where the surface actually provides more gains. I will go fast on that. This is the formulation of the problem. We have defined the formulation like that, incorporated the constraints that are related to the low rank and the sparsity of the channel. And at the end of the day, what has been showcased is that we can provide very good channel estimation performance compared with baseline, which is actually Gini, implying that you can estimate everything like RIS being a multi-antenna receiver. But the cool thing is that we can do it even with one RF chain. Please emphasize this number one, and with a reasonable number of training slots. And the number of training does not depend on the number of elements of the RIS. Of course, if you have the flexibility, you can afford larger number of RF chains. You can actually improve the performance of channel estimation. Of course, you can also do channel estimation with this simultaneous tuning, as I said before, and sensing surface. We have a model of operation for this surface. In the economy of time, I will go fast. You can see the relevant publications. Recently, we have the technical paper related to that, where actually the vision there is, due to the fact that we can do sensing at the surface, we provide a mechanism, both the RIS estimate the RIS to the user channel, the base station estimates the reflected channel, and we fuse this estimation. This is what you see here in this combined channel estimation metric, in order to boost the channel estimation actually accuracy. And actually we can do that. And we optimized both the configuration of the RIS for reflection, both the configuration of the hybrid RIS for reception, for sensing, but we also jointly optimized the reflection, the power splitting operation, if you recall, that determines which amount of energy gets tunably reflected or gets sensed. And here you see actually that with a 50%, let's say, splitting ratio, you can have a very good actually channel estimation performance while operating in a tunable reflection simultaneously. There are actually various applications of the RIS. I would be fast here, sketching the applications and then end up where people have been using, as I said before, RISs in multi-cell setups. So you can consider this is the case where there is a commonly, right, a commonly used surface by two base stations, could be different operators or even the same operator, trying to provide coverage to people, to users that are lying in the same edge, or even, this from a recent discussion that they had an operator working on a project like that, or even reducing the amount of handovers, which is a critical issue, right? And it has certain implications in terms of the power operation of the network. People are actually another extension that are envision multi-cell with multiple RISs, so they're different operators, right? Each one using his own RIS, and how we orchestrate them. Of course, you can envision that the overhead, the channel estimation, and the knowledge that needs to be incorporated there is of paramount importance, although people mainly are looking at the optimization of this. Another piece of work that I would like to emphasize and only sketch the result is that there are various people, including my group, that they're trying to unveil the potential of the RISs in terms of the performance boosting they can provide using dedicated models on that. Here, in this work, we are using tools from statistical physics, actually from the replica method and random matrix theory, in order to come up with a closed form expression in the large antenna regime that showcases the capacity gains that we can get in an environment where we have a transmitter, receiver, and multiple RISs. We have some obstacles there because with the model that we use, we can actually play with different versions of the correlation matrices, implying rich scattering, low angular spread, and large angular spread scenarios. Rich scattering and pure, actually the opposite, pure line of sight and rich scattering respectively. So we came up with a formula there, which we have used to perform optimization, typical optimization tools, but also we use it to provide closed form expressions about the optimization of multiple RISs, profiting from this expression. And what has been actually showcased, which is super crucial here, is that the following. You actually profit from the here I want to emphasize the x-axis, so the angular spread, which means low angular spread, quite specular directive channels, high angular spread, rich scattering. What this figure showcases, there are two major things. One related to the optimization of the risk that tell us that you profit from the optimization of the RISs when you are in cases of low angular spread, which means that channels that are quite directive. But when you, on average, this is an average metric, this is the ergodic mutual information in NATS. But when you're thinking about rich scattering scenarios, a large angular spread, on average, if you're using a random configurations of the risk or even doing nothing, right, you will get the same performance while doing optimization, which means optimization does not provide any gain in rich scattering scenarios. Just use it and change the configuration at random or let geometric optics do the job. But when you are in low angular spread, optimization plays a huge role, and this is the gaps that you see between the pairs of curves that they have the same color. But in this case, on low angular spread, our closed form solution actually gives the exact result, which is the same with the typical sophisticated and actually time-consuming optimization, which implies at the end of the day that you can use our closed form expression, right, to tune the surface, the reflection coefficient of the surface with certain implications, actually boosting the hybrid risk case that I said before, because in low angular spread means that you can estimate something related, for example, to the principal AG mode of the channel. This is really, you can do it easily with a hybrid risk. Just some implications there. Other ways people are thinking of how to orchestrate scenarios where we have multiple RISs. We have a very recent survey that we devised deep reinforcement learning tools to efficiently optimize various RISs in a typical scenario where we have a base station with multiple users. In this paper, we overview the recent literature of formulating actually the actual problem here to orchestrate a risk-enabled smart wireless environment. We provide the formulation as a reinforcement learning problem. We actually we have implemented, we have the codes available online of the state of the art, but we have also devised two novel actually approaches that we have borrowed from the reinforcement learning literature, which actually achieve the same performance with a sophisticated, DQN algorithm, but with nearly 50% less of the overhead that is required by emphasizing on some key properties that we have identified. I don't want to go into the details in the economy on time. Of course, people are also using, apart from reinforcement learning tools, to use typical supervised learning approaches. Here you see the first set of works that we have done it with my group there, international group, where we have used the locations of the user in order to do supervision of learning and then applying on the online phase to optimize the surface. Another key application that will again go fast in the economy of time is to use the RISs to provide secrecy, right? How you could do secrecy. But the interesting thing here, and what I want to sketch and emphasize here, that any technology that has a potential, right, can be used apart from the, let's say, the correct way, can be used also in a malicious way. So in this paper, apart from trying to optimize the risk together with the configuration of the multi-tenant transmitter and receiver, we also thinking of a case where this is the malicious risk used by an eavesdropper, which tries to optimize it in its own profit in order to eavesdrop information. I'm not going to go into the math details where we formulated the problem, and we actually focused also on optimizing the eavesdropping part with what this guy knows. He knows minimal things related to the legitimate link, but also we optimized the legitimate link on what he knows about the eavesdropper, and we assume that it does not know the existence of a malicious risk. And we ended up with a formulation, right, and an optimization approach, which showcased that at the end of the day, I want to stay at the end result is the following, that if you're trying, you can optimize your risk using a legitimate risk, using artificial noise, configuration of your beamformer at the transmitter and legitimate receiver. But if there is a malicious risk, you have a serious issue. There are regimes where the information will get eavesdropped. But if you use, I mean, the case where you use only artificial noise, if you use an eavesdropping risk and with our approach, you can secure that you can always provide secrecy, you can always provide under the constraint that you have a legitimate risk that has 5 times more the number of elements of the malicious risk. So there are various in the place that one could consider there. Let me now sketch in 2-3 minutes, Amit, I will conclude. A little bit related to the localization of the risk, and I want to emphasize what's the difference when we don't have a risk. So what is happening TPP up to now, standard localization. By the way, please, you have to know that localization and sensing, they're supposed to be actually one of the key, let's say, requirements for 6G. Actually, we're looking a lot at these applications, as I said, for standalone and non-standalone operations. So in 3GPP up to now, we require at least 3 synchronized base stations to provide localization. We require line of sight connectivity to the base station, and there is a limitation related to the multiband interference. I mean, in multiband scenario, it's hard to localize. What we can do with RIS, what RIS actually are enabling when we're thinking about localization. They can provide localization even in cases where we don't have line of sight by using multiple RISs or when operating in the near field case where I showed you before. Recall that the RIS makes sense when you put it closer to the transceivers, which means the nodes that you want to localize. You can provide localization even with one single antenna transmitter, one RIS, and operating in wideband. There is the synchronization in nature due to the fact that everything is happening in the RF domain as far as the risk is concerned, and it's separable from the uncontrollable multipath when you have the RIS, and you can actually, this enables localization even in multipath conditions. But we can even boost, even in cases where we can localize with 3GPP right now, you can even boost with a RIS, I mean, provide even enhanced localization with uniform coverage, and you can provide the boosted areas of localization. Here you see a typical example, and this is for a recent survey that we have provided. It's actually under review on the TVT magazine, where you see on the left, a case where you can provide localization to this couple actually on sitting in this specific place with a laptop by using a RIS and operating in the near field. or even in the case where you have two base stations without a RIS, you cannot even localize. So there are certain cases where you can provide localization, and this is actually sketched in this slide, where I would like to emphasize the extreme case. You can even have the recent paper that is actually surveyed here that we have provided lately. You can even self-localize. You can self-localize yourself, your mobile handset. If there is a risk, you can communicate and you can get synchronized with it, even with zero base stations. So there are certain scenarios, right? You see on the top, you see a line where there's localization when you don't have RISs in SISO, MISO, SIMO, and MIMO systems, and cases on the bottom where you can enable localization by using RIS in cases where you could not use it without a RIS. And this is actually elaborated in this paper. Of course, you can use the RISs in receive mode to provide localization, and this is a recent work that we have lately provided, analyzing the position error bound and providing a comprehend sensing algorithm to provide localization, even in cases where we have multipath. These are some results that showcase the feasibility, and this is a heat map that showcases. Here you see the placement, you see only the 2D part, it was 3D, the placement of 3 RISs, receiving mode. They receive with a single RF chain. We fuse the results and we provide localization. And here you see the position error bound. The placement determines which is the area of this room here. It was 10 by 10 meters where we can provide boosted performance of localization. Of course, and I'm about to conclude, you could use also, these are really fresh work. We are providing actually a Signal Processing magazine with an overview regarding that of risk-edited radar detection. So people are using RISs to provide detection. This you see an application here by a group of very good colleagues from Italy, where the target you want to find its direction, and there is also an extra path which is being induced by the RIS. So the radar, apart from illuminating towards the direction where the target could be, right, it illuminates the known direction of the RIS that will create a reflection, and it gets back all this plurality of the reflections, and this can enable it. It provides the required degrees of freedom to enable localization. You can even think some other recent works of doing self-sensing with RIS equipped with sensors. I mean, RISs, this is the different terminology, right, of RIS, RIS is here, where you have an RIS having some sensors that can be used to localize, for example, drones on either account. So this is the combination of a typical surface with sensors to provide target sensing, or even do simultaneous localization and mapping without base station. It's something, an ongoing work that we're working right now, and we're trying to profit from the fact that the RIS can also sense apart from reflecting. Concluding, I try to convince you today that RISs can boost the performance of wireless systems and enable various applications, crucially in a cost and power efficient manner. But however, there are several challenges that need to be addressed for the technology to make it. I want to emphasize for 5G advanced. Why? Because they're a smart repeater which has certain notions of the RIS technology. We require information theoretical methods to characterize the RIS and part wireless channels. As I told you before, we have been using a lot the cascaded channel model, but this is quite challenged, and we need actually to go even further. And there are a lot of works being done on the modeling part. One of the first works that incorporates fading, which actually the realistic case, I try to sketch the work that we have provided. Of course, I can discuss offline further details. And of course, what is happening in terms of interference channels when we have RISs, interference will also get boosted. We need to find right models on that, how we model cases where we use RISs to do over-the-air computing. We require still algorithms and networking schemes for realizing communication with RISs, and of course, how to orchestrate multiple of them and how to optimize them. The interaction of the RIS elements when placed very close together, these near field effects for communication localization are still open, and we need to incorporate the interaction with the channel matrix. We tried with this couple-dipole formalism that which actually relies on French principles of physics, and definitely we need, of course, to come up with approaches, with methodologies to provide optimal placements of RISs for communication, localization, and sensing. Doesn't necessarily mean that an optimal placement will work for all these three applications. I would like to thank you, and I'm quite open and looking forward to questions. I want to emphasize that it will be my pleasure. You can use my mail to interact even offline for anything related to the topic, the talk, right, and my research. Thanks a lot. Amit, I'm all yours.
Yes. So thank you, Professor George, for your talk. And it's a quite interesting and quite nice talk. You had covered quite large and vast variety of RIS and its various applications, starting from signal processing approach to multiple applications. Here at our lab at IIT Patna, also we are working on various aspects of RIS, starting from energy optimization to localization to channel estimation, as well as capacity enhancements. These are the aspects on which, by using RIS, we are currently working on. Only the thing here, what we are more emphasizing is how we can go for its hardware implementation as well. As of now, we are targeting sub-6 gigahertz band of 5G, and that is 3.5 gigahertz in India. And we are trying to incorporate like how we can go for its hardware implementation. In the latter phase, we will be thinking of going to millimeter waves, like at 28 gigahertz and 38 gigahertz of its application. So this is some of the view at which we are working here at IIT Patna in our lab. So now I will take some of the questions from audience. So the first question from Vardon is, he is asking, does the angle of arrival of the incident signal affect the passive beam forming solution? If yes, is it right to assume channel reciprocity in RIS added system?
Actually, this is a very, very interesting question. Strictly speaking, and this is something that we try to incorporate, and this is actually incorporated in the model that I showed you before. That's why it's really problematic with these cascade channel models. The model, the received signal, will depend also on the angle of incidence. This is actually known from measurements, and this is something that we are trying to encapsulate into the models that are quite simplistic. So definitely this will determine the received signal, which means will determine the channel model. So the answer is definitely yes. Now, the reciprocity, I mean, naturally, it comes into this case. The fact that you have this interrelation with impinging angle actually ruins the reciprocity. So it needs to be incorporated in a way, meaning that if there is, let's say, a channel which can have this form with a specific impinging angle, and then you send it through a different direction, strictly speaking, this needs to be incorporated. So my answer to the second part of the question is again, yes. So this needs incorporated, and indeed the reciprocity is questioned related to propagation with RISs, for sure.
So,
which means, sorry, Amit, this needs, if we have the right models, which is still a pending work, right? If we have the right models, this will definitely be incorporated on the optimization of the passive beamforming, of course, just to also clearly answer to that.
Yeah. So another question is from Suchitra Tiwari. She is asking, can you please give an insight into the aspect to keep in mind when designing RIS at millimeter wave frequency range?
Insights when designing, eh? This is what you said, right?
Yes, yes, yes.
Okay, I will try to give you insights from the algorithmic perspective, and of course from my various interactions, as I said before, that I have with colleagues working in hardware. I mean, my group has been actually working with at least 3-4 groups around the globe, fabricating RISs in various frequency bands. Is actually part of this European project that I'm working also. People are working on fabricating in sub-terahertz. From the algorithmic perspective, I want to emphasize, at least in my opinion, one crucial thing is the actual operation. I mean, when it makes sense, when are they going to be used? it seems that if we think about the characteristic of the channels, right, they will be used mainly for channels that are quite specular, which means quite directive, right? This implies that they will be used as coverage extenders, I guess, or for providing localization and sensing. This implies that the lambda over 2, right, does not really make sense. We need to go into cases where you place them much closer, right, as much as possible in order to maximize the beamforming gain, right? I mean, ideally, we want very directive beams, at least when we're going to apply them in the final operation, right? I want also to emphasize there, but there's always the initial phase where these guys, they need to be initialized in a network, right? So it needs to connect with them. We need to see them. So probably we need also some wide beams to do the initial access. So my insights are related to that. So the operation is going to be on quite specular channels, which means that the placement should be close from what we have seen from all the various works, right? And we should have beams with large beamforming gain, but also ideally some hierarchical beams in order to enable the initial access when we're thinking about communications, right? But also various localization approaches if we want to do them, to use them, let's say, in a short range radar mode, right? So a RIS could be used to sense its nearby environment. So my insights related to the fabrication will be related to that. I'm sure that you hardware people can definitely understand what is, let's say, what is the actual technology in the fabrication that will boost, I mean, these beams to be effectively designed. I mean, their main lobe, I mean, the ratio between the main lobe and the side lobes, all these things. But I want to emphasize once more that I really believe on a RIS that is capable to perform a form of sophistication of sensing on its side for the reasons that I tried to explain today. Because the overhead to orchestrate it is going to be large, especially when it's going to be in-band orchestration. I'm not talking for a RIS where you place it in a room and you have an Ethernet connection and you can do things easier, right? So there, in a way, it's an extension of what you can really do, but you will need the circuitry to provide this form of control that you would like to orchestrate it, right? So this is what I want to emphasize.
And the last question from Rakesh Ranjan. He is asking, in on-off channel estimation, there is some delay. Can you tell how to mitigate delay or channel estimation for delay selective devices?
There's a major issue. The delay, exactly, the overhead that I said before translates to delay. Delay has actually two interpretations. Delay means that you might get to a case where the channel is outdated. I guess the question is exactly on this point, that you spend a lot of time to estimate something which is going to get outdated. So this is a serious issue. My opinion is that this on-off is not going to work. It's not going to work. Because it will, the delay, you will get outdated and you will have a serious issue. My personal opinion is that the operation would be towards the direction of being capable to sense something. Each optimization, as I said before, these are actually my 2 cents regarding all this technology. Each optimization makes sense to specular channels, which actually this emphasizes the fact that you can do some sensing. You can find some DOA, right? Some DOD. And this you can do it with some basic sensing. As I said before, we do it with that paper. We have done it with only a single RF chain, which means this can boost, right, in terms of latency, the sensing, the estimation part, right? The knowledge of where you want to do the reflection. And then you go, boom, you do the reflection. So I'm expecting at the end of the day that the operation that will treat the delay is going to be something towards this end.
Yeah. So in the end, anyone else, if you have any questions, comments, please let us know. Okay. So it looks like there is no more questions and comments. So again,
Amit, just to say something to everybody. Of course, once more, thanks for your attendance. Hope, you like the talk. It will be my pleasure with all of you to consider establishing collaborations to answer to your questions. The chat is going to be off when Zoom will close. So any comment or proposal that I didn't reply, please send me an email to this email that you see there. You can find my website, all my details to interact further, right?
Yes. And
thank you once more, Amit.
Yes, and just for all of your information, that is, we are going to have very strong collaboration in future with Professor George and others team. So here also in the meeting, just requesting like those of you who really want to work on the topic of the interest may contact us at any point of time. We are more than happy to reply the concerns and will be always to help you at any point of time. So from our side, to all the attendees, thank you all of you for joining from wherever you are. And Professor George, from my side, thank you very much. And again, we will be in touch in some other mode. We will discuss other aspects there. Okay. So thank you from our side.
Thanks a lot.
And from India, it's namaste. Thank you all.
Bye, guys. Hope to see you face to face soon. Bye. Bye.
Sure.
Bye.
Okay. Thank you all. Bye-bye. Good day.
Bye.